episode. This should be number, for Ozzy it's number 5. So let's start with the usual ritual. Let's go to the browser. Okay, so as you all know, please like, subscribe to our YouTube channel. I always say this, but just to remind you. I remind you also that under each video there are links to the code, to the videos, to the playlist, etc. So please click there. The link should take you to one of these directories or other directories depending on where you're coming from, but normally it takes you to the Mega drive, mega.nz, where I have my storage in relation to this. Each episode has got its own zip file or source code related to it. As you can see, the sources for the first 3 episodes related to Ozzy are also there. Okay. May I remind you that there is my Facebook page to like, follow, etc. And same, there is my Facebook Phase 101 group. Same thing, we have the Commodore Facebook group, so please subscribe to the groups, the Phase 101 and the Commodore Dev, like, etc. Guys, I'm not trying to beg, okay? I'm just asking you, if you want to help me, this is how you can help me. If you want to get in touch with me, you want my help for anything, you can write me messages on Facebook. I take time. I answer though very quickly, normally on Discord. So please join Discord if you want a quicker response. I did have people that complained on Facebook how long I took, but I'm not on Facebook all the time. Also, Facebook, the latest interface is so annoying. And last but not least, for those that do not like Discord or anything else, you can also text me and join the group on the Phase 101 group on Telegram, and you can message me there. As far as I know, that's basically it, except for if you want to support us, now you should know there is Patreon or Coffee. Right now you will unlock 73 videos on Patreon or Coffee. To be fair, it is 75. There are 2 that I haven't acknowledged yet. But yeah, they are a mirror of each other, so I do not I update both. That's basically it. So, hello Ozzy, can you hear me?
Yes, I do.
Okay, perfect. So let's load your first example, and I need to switch on your...
Wait. Before loading, I sent you a PDF on Telegram just last minute, and I would like to use it
okay.
just the first 4 pages.
Okay, so wait, let me switch on your webcam. Welcome Ozzy to the stream. And now you said you sent me on Telegram a file. So
yeah, just to help for an introduction, because really it has been a month, I think, since last time. I don't remember anything.
So I do not see any files on Telegram. Did you send it
Mm,
somewhere else? I don't have any files on Telegram.
wait a moment. Let's see. Uh,
Let's get the code so they see something on the screen. Yeah.
I can. Oh, come on. Telegram is not working now. Okay. Oh, yeah, you're right. Maybe I sent you with some other protocol. I will send you again on Telegram. And that's it. Sent.
Okay. Now I got it. Now you did send something. Okay. So I need to open it now. So there you go. Episode 5.
Horses. So, just let me remember something. I remember that last time it was August, and I
Yes.
talked about, I think, vectors.
Vectors. Yes. You talked about vectors.
Yeah, and I just listed my vectors routine, nothing fancy, and I mentioned that I took inspiration from this implementation from the book of the Nature of Code book by Daniel Shipman.
Yes.
And I do remember that I just discussed the chapter 1, which was just a basic vector introduction.
Yeah.
And now that we are in September, I thought maybe it's time to use the vectors and just be creative and do something
Yeah.
cool with vectors. So
Okay.
this is why.
So
This is
basically, just for those that maybe haven't been following, or Ozzy has got a framework. It's called AProcessing. Okay, it's a framework to write demos for the Amiga. Okay, and we are showing. I mean, Ozzy is showing how to use his framework. Okay, to write, let's say, simple demos or simple things right now, and what features it has. So basically, yeah, I know somebody that uses processing, but that is processing in Java. He converted that for the Amiga. So there you go. Some of the functions, not all, of course, but yeah, honey, that's exactly it. Not to interrupt anymore. Ozzy, in your hands.
Yeah, just interrupt me whenever you want, no problem at all. This A processing is not a clone of the original processing, which is written in Java, and of course would be impossible or at least very hard to port on the Amiga. And this is just my view, my implementation of the main ideas, main concept, but really the project has nothing to do with processing.
Yeah.
What is linked is just what Daniel Schiffman, it's a popular YouTuber, is doing with his lessons. And when it's doable, I try to just write my implementation on the Amiga, reusing the same concept. So I'm not copying, it would be impossible. I'm just reusing the names of the function when it's convenient. But really, that's it, nothing more. So just taking ideas, and if you followed my last episode, I stated clearly that I took inspiration for this from this book. I don't know if if it's visible right now. It's the book I bought on Amazon. It's from Daniel Shipman. And of course,
Hold
inside
on.
here,
I
there
have it
is
too. Hold
nothing
on.
Amiga related.
There you go. I have it too.
Yeah, it's the very same. And the book is also available online for free. So everybody can enjoy it. And so this series of talks are just my understanding, my interpretation of this book. Last time I discussed chapter 1, which is a basic vector introduction. Now today I will try to do the first 3 paragraphs of chapter 2, which is quite heavy, quite complex, and it will take a while. I don't know even if I will pick off all this bells and whistles or this chapter. But I just want to mention the main concept here and there. Of course, if you are interested, please buy the book or follow Daniel, on YouTube and all the other social media. So, okay, you can go to page number 2, which is, I think, the most important slide of this night.
Is it this one?
Uh, yes, what is a force? And this is the very same definition that was copied or stolen from the book. A force is a vector that causes an object with a mass to accelerate. This is the definition that is using Daniel, and it fits to me and makes sense. And we are in luck. We discussed the vectors last time, so we already know what is a vector. So it's an object with magnitude and direction, and we know how it's represented. And there is a whole video talking this by Daniel, of course, on YouTube. And from the Amiga point of view, it was my last time here. And so this is why I started implementing the vector operation, because I wanted to use vector to represent forces, like gravity forces or wind forces or whatever force you need. I was thinking, for example, when you coded the Rex and you coded how the jump behaves, these vectors came into mind to me, and I said, wow, this is a perfect application, because when you jump, the dinosaurs is jumping. Maybe you can apply a force to the dinosaurs, and the dinosaurs, the whole math behind could do the job to calculate the trajectory real time without using lookup tables or some complications. So like just me brainstorming, I use for other applications. And one of these applications is what we are going to see in a few minutes. Please go to page number 3. And the page number three is just...
Wait, I think I skipped. There you go.
No, it's with the one before. This is okay, this one. And this is just a refresher. I hope you won't get mad at me if I'm repeating myself. You switch the slide again.
No. So I told you that this is what I had, and then after it, I had this, the vector ops in AProcessing. That's after.
Okay.
Yeah.
Okay.
So
this one.
Yeah, that's the one that there is after the one that you.
Perfect.
Yeah.
This is just 2 words on this slide, please, and then we can continue. Mm-hmm. So, as already stated last time, these are the most common vectors operations that you can find on processing, and you also can find of I think every other languages or frameworks. And what I did, I just changed the name because, of course, I don't have object-oriented language. I can't copy. I can't do anything. Even the processor is different. So what I end up with is with a bunch of macros or function that just try to mimic at best that I can the vector operation. And as you can see, I didn't implement all of them because it's a very huge job. I just implemented in some way what I needed for my demos and for my software in general. And you see that the addition and subtraction and multiplication has been implemented. And if compared to last time, I put some starts asterisk to the limit. And this is why I tried to implement also the limit function on my own. Still is not on the main library because, as you probably know, I have this behavior of testing and testing before merging into master. So I have to try it in different scenarios how this limit is working. But we will see a preview today. Please go to the next page.
Mm-hmm. Just 1 second. For those that want to see the book, I send the link, but this is the page that you should see about the book. Okay, you can also buy it. Okay, so it's on Amazon. It doesn't cost much, but you can see the chapters here. Okay, you can see the chapters. So last time we did vectors, and today we are doing forces. Okay, and this is what we have. So
if I may just go off topic again, I heard that Daniel is working on another book. It's still related to the nature of code, but it's just revisited. I don't know
if
it will be.
I heard the same too. Yes.
Yeah. So this book is quite old. I think it's 10 years old at least.
Yeah.
And what I know, soon there will be another, maybe bigger, maybe with corrections. I don't know, but ask Daniel if you're interested. Right now, this one fits well for me because the calculation, the math behind is very simple. And this is what I need for the Amiga. I can't represent a real physics engine on the Amiga because I don't know how to do it. I'm not a physician. But this method, this Euler integration, works quite well because just involves a very basic mathematics, and it's quite fast even on an Amiga, which is a slow computer if compared to our everyday computers. So just for me, it's perfect. If you read the chapter 2 of the book, you find this definition, which is about the Newton's first law, which states that an object stays at rest and the object in motion stays in motion, which is a quite cool statement. Of course, this is not very accurate, but it gets the idea. If you have an object and you don't apply a force, the object is still, it doesn't move. If you have an object with an initial velocity of x, can I go on? Because I'm seeing that there is an advert.
You are getting adverts?
Yeah, I'm seeing an advert, and I don't know if I can go on.
Yeah, you can go on.
Okay. So I was talking about this. I just don't remember what I was talking about. Okay, the Newton's first law. And if you think, for example, we are in space and there is an object with an initial velocity, and there is no force. So this velocity is retained by the object. So you have some other force to stop it. And this is the main concept of this law. Of course, Daniel extends this concept too much. He starts to talk about the net forces, so the sum of the other forces that must be balanced or unbalanced. But I think this is too much to take at 10 p.m. So I want just to state the main idea, the main concept of this law, because we will try to simulate on our Amiga this concept. And please turn on the page again, and this is the last slide. Should be about the Newton's second law.
Yeah.
Okay. And this is just a formula, and it states that the force equals mass time acceleration. And if we can put it in another way that it's better for us, it's the acceleration is the force divided by mass. So in the next examples, I was trying to simplify this and just assume that mass is equal 1, like Daniel did on his YouTube videos. And so this gives us the formula, which acceleration is equal to force, which is pretty quick to implement, even in assembler on the Amiga, and it's very fast. Of course, I will try maybe in the future do something with mass, so we can see different objects with different masses. How do they behave when a force is applied on it? So at this point, I think we can just go to the Visual Studio Code and just see my implementation.
Shall we run it before? Shall we run it before you explain the code? I think it's better, no?
Yeah, you do it if you can, please. Okay, this is my silly implementation and very buggy, but I think it gets the idea. What I'm doing here is I just create two squares. Let's call it movers, because they can be represented with any polygon or every point or every sprite. And I apply a force, which is the gravity, on both of them. And then there is a simple routine that checks if the position is the bottom of the screen, and then it make them bounce, and that's it, nothing more. But just to get the idea how a vector can help us to create this movement without any pre-calculation or any lookup tables. And the implementation is very simple, and I think I can show you what I did in the code. Okay. So please open Visual Studio Code, and again, I'm just reusing always the same file from the Fabio Ciucci's book, Lezione 8N, I think. So I'm just reusing the startup from there, and just reusing the very same copper list. So really nothing changes from last time. And what I did, I was just to give some order to the code and give a structure. And where I want to start here is at row 97. Can you go there, please? Mm-hmm. Okay, so what I figure out this time, of course, I can't use an object because objects are, let's say, a feature of object-oriented programming. I don't have object here, but what I can do, I can just allocate a portion of memory and I can just create something like a bob. For example, with offset, I can define a data structure and here is where I load values into this data structure. So I load all my values in the data register, for example, the D1 and D0, and this is the initial position of the square, and D2 and D3 represent the vector that represents the velocity of the vectors, of the vector. D4 is the color in the index color. D1 is mass, and I will always use 1 to simplify things this time. And D6 is just the size of the square, nothing more. And then I call this init mover that just copies this data into memory. Of course, this is not the proper way to do it when you program a demo, because we are wasting memory and we are wasting time. We could just say DC dot value minus 20, comma, minus 8 divided by 2, and etc. and so on. But I just want to do this because I like init function, and makes sense if you are at this stage, uh, just to get the idea and to init quite quickly things. So here I created these two movers object, but which again, they are not really object, they are more data structures. And then I have at line 91, there is a gravity, and a gravity, it's a vector, a 2D vector, and this is the force, the vector that represents the force of gravity, the gravity force. And the goal of this little demo is just to see how we can apply gravity to each of the mover. So each frame, the movers will take the gravity object, the gravity vector, and do some math, some calculation, and that's it. And how do we do that? It's very easy. Please go to row row 139. And this is the main loop, and as you can see, it's just we are cycling for each mover with the dbra, and for each object we can there is this, we load the gravity, the gravity address into A3, and then we apply the force, and there is mover apply force function. All it does is it takes the gravity and it applies to the mover object. Then we have the mover update function, which updates, the main goal is to update the position of the square, of the mover object in memory. And the mover show function, and it's very easy, and we will see all of this function in a moment. It just draws a square with my routines, which, using translate and using draw square and etc. We're using the right color and so on. And the function are implemented at let's say row 218. So please go there. And maybe you can recall this code from last time. It's the very same code. What I'm doing here, I just set A1 and A0 and A1 address register with the location of the mover. The base is at A0, which is saved into A2. And then we call add vector. So we add acceleration to velocity, like we did last time. Nothing changes. Then we add the velocity to the position of the object, and the code is always the same. You put the source into A0, the destination into A1, and you call add to the vector, and the result of the addition will be placed in the second operand, so at the memory address pointed by A1. Then I reset the acceleration every frame. This is, let's say, needed for this method because every frame we have to reset it, otherwise it accumulates over time and the square goes crazy around the screen. And lastly, there is just a stupid check, and I say if the y position of the square reach is greater than some arbitrary value, that here is 8 divided by 2 minus 20, then we must bounce, simulate the bouncing. And how do we do that? Using the neg instruction. Neg instruction is a Motorola instruction, so you don't have to figure out anything. It's already there. And what it does, it just multiplies for -1. So you just change the sign of the y component of the velocity. And that's it. For example, if when you hit the ground, the bottom of the screen, at this point, if the velocity is, for example, 100, then you get -100. So the new velocity is -100, and we have a big bounce toward up of the screen because, again, when you subtract, you go up to the screen, and when you add to the y position, you go down. So this is the main concept. And maybe you are wondering how it's possible that the squares comes to an end. The bouncing movement is 0 at a certain point, because reading the code, it seems that, okay, if you get 100, you output to -100, so the bounce would be an endless loop. And this is one of the problem of this method, because we are not just seeing at the continuum space. When there is a certain point that you go under the screen, so we are just resetting the position and we are losing pixels. And this is why the bouncing gets smaller and smaller over time. But it's not a big issue for me because I like it and it's more realistic from my point of view. So I like this way. Of course, there are, if you want to an endless loop, so the bouncing go forever, you have to tweak the code just a little bit to make the math correct. But this is just to show the main idea. So this was the mover update function. Later you have the mover show function, which is exactly what would you expect. It just it's at line 250, so it's very near here. Go down just a little bit, yes. And this function is very, very trivial, and you can guess what it does. it sets the color of the square with the stroke, and then it loads the position of the mover into D0 and D1. So these are the coordinate. And always remember that the screen is translated into the center. So 0.00 is actually the center of the screen. So it's width divided by 2 and width divided by 2. So 00 is exactly the center of the screen. And then we wait for the blitter because the previous mover could be not completely drawn by the blitter. And then we just blit the square. And that's how it works. Nothing really fancy here. And all this stuff has been showed a long time ago, I guess, on this channel. So if you didn't see it, go back and just take a look how does it work, this translation and these drawings. Then we have the next routine is the mover apply force function. And this is where I try to implement Newton's second law. And of course, this is quite trivial. What it does is we apply the external force to the mover object, to the square. In this case, the external force is the gravity. So we just we expect on this routine that A0 points to the gravity. No, A3, no, not A0, A3. And then we just call again every time the same routine, which is add to the vector. So the gravity gets added to the velocity, and that's it. And the clear top is just clears the screen between each frame. And I think that we discussed all the relevant part, how I did it.
Mm-hmm.
And again, these are the very same concept of Daniel, but on assembler. Maybe someone can find this useful, maybe for a game or just for a demo. You can use vector for whatever you want, really. Very flexible.
Just one thing I want to say, but it's in relation to the previous videos. Maybe you noticed macros like enable clipping, create 2D vectors. These are all things that we discussed in previous, and of course we are not going to discuss them again. But no, please know that we are building. It's a building block. No, on what we did previously, we are adding stuff on what we did already. So can I pass to example number 2?
Yes, of course.
Yeah.
In the meantime, I will take a sip of water.
Mm-hmm. And shall I run example number 2?
Yes, please do it. And remember that when you run it, you have to keep pressed the right mouse button and release it.
Yeah, this one I didn't see. So you sent me the code when I was still working. So I didn't get time to do it.
Again, very sorry for this late last time.
The first one I did see, but the number 2 and number 3 I didn't see because I was working when you sent them. So
it's the very same example. Really, nothing changes. Only one thing, and it is very trivial.
So I need to continue holding the left mouse button when it starts.
Yeah,
Okay.
Just keep it pressed.
Oops.
And then at a certain point you release it.
I see.
Exactly. So the point here is, do you remember when I started talking about the first Newton law? And I said that these objects, if they are at rest, they stay at rest, and if they are in motion, they stay in motion. And what I want to demonstrate with this stupid demo is that when you press the right mouse button, you are using apply force. You are applying the gravity to the object, and then when you release it, you are not longer applying it, and so the initial velocity is the same. You would expect that maybe that when you release the button, the object will stop moving, but that's not the case because, as I said, Newton's first law is just stating that if it's motion, the object is in motion, it just keeps moving unless there is an opposite force equal to stop. And this is the simulation. Of course, it's not very so spectacular probably, but I think it gets the idea. And if you go to the code, I think all it does here is let me check. If you go to the code at line 138, you can see the change. And bit test to DFF 0016. And this is the test to see if the right mouse button is pressed. And if the bit is set, it means that the button is pressed. I think at least. And if not, you just if it's pressed, you go to no gravity. Otherwise, you call the apply force function, and that's it. So this is just to better understand what this mover apply force function is doing in practice. Another thing that I'd like to show, it's at row 296.
296.
96. Okay, limited to the vector. And let's say this is new routine that I think I should put in my AProcessing. And this is important because if you remember last time I talked about set magnitude. So we are setting the length of the vector with set magnitude. But limit vector, it works differently because it just checks how much is the magnitude of the vector, and if it's more than a certain threshold, it just limits it and it recalculates the magnitude. If you strip this, the squares can increase their velocity and the momentum, and they go crazy around the screen with a very high velocity. But with this, you can limit and you can say, for example, okay, if the velocity is greater than, let's say, in this case, it's 15 pixels per frame, then you limit. So you say, okay, it's no, you just can say, okay, it's hard to explain, but you just put a limit, put a cap on the speed of the movers, and this is why I implemented this stuff, because otherwise, since the gravity is quite strong, because the gravity here is 1 pixel per second, and since it accumulates over time, after 60 seconds, it starts moving very fast. So what I did here, I wanted to limit the speed. So 15 pixel per second is the maximum allowed limit. If you go more, you can just get 15 per pixel. And of course, this must go through all my tests and try what happens with negative numbers, with very high numbers in case of overflow, just to understand if it's behaving like like I want. And that's it. So please go to the third and last example, because we are running out of time, I think.
That's okay. That's fine. Okay, so third example. Unless you need to go, I can continue, no problem.
No, I don't have to go. I took the whole night free, but I don't want to annoy the viewers, because it's quite late.
No, actually, we
just for that.
Actually, we need to annoy them so that they learn.
Hopefully.
So yeah. Okay, so I'm going to run the example, and then you can
the third, please. The third example works like the second. You just keep the right mouse button pressed.
Okay. Mixing those with Amiga. Okay.
Yeah, this is the very same example, but this time I just used two forces.
Yeah.
So the second force is the wind, and when you press the right mouse button, the movers are attracted to the right of the screen, because the wind is a vector which is pointing to the right. Of course, it could be cooler. Maybe we can say if you press the left mouse button, the wind is -1,0, and if you press right mouse button, the wind is 1,0. But I didn't have much time to do cool things, so this is what I got.
You can ask questions. Yes, well, please, by all means. Actually, I'm quite liking this one. It's giving me an idea actually for something. But yeah, okay. Is it all of this done with integers only? I leave. I know the answer to this, but I leave Ozzy to explain. So the question is it all of this code done with integers? So
this is a very dark territory. If you follow the last stream, you know the answer. And the answer is that it depends what you are referring to, because we are not using FPU to do the calculation. So in this sense, I would say yes, I'm just using the integers. But as you already know, if you follow last streams, I use the fixed point notation. And what I usually do if I need decimals, I just reserve the less the six less significant bits for the decimal part, and the other 1 bit for the sign, and all the other for the integer part. This is what I usually do. For example, if you want to see the velocity or the gravity to be weaker, we could use this method and say the gravity is not 1, but instead is 0.5 or 0.25. This is doable with fixed point notation, and this is something that I did, I think, 2 streams ago, if I'm not wrong. I don't remember.
Yes.
But in this example, actually, I'm not using decimal at all. I'm just using integer, and I'm using all the data register like integers, so not decimal part at all. And this is why they are moving so fast, because 1 pixel per second is quite a lot of gravity in a PAL low-res screen. But of course, there are some tweaks you can do. As I told you before, we can use again my limit function. We can, for example, set us a low limit, 5 pixels per second. You get a similar result. Of course, the wind and the gravity can be changed, but of course you can't go less than 1, because I'm not using a fixed point notation here. But it's doable, of course. You just have to multiply by 2 elevated to how many bits you want to reserve, and then normalize to integer when you have to compute the real location on the screen. So it's not very particularly helpful, even if the 68 processor really it is very low to shift bits, because it depends how many positions you have to switch to shift. But it's still doable for a small project. My goal is always to avoid using lookup tables and just try to reuse as much as possible the M68 instructions. I like real-time calculation, and doesn't matter if the result is poor and if there is no graphic, or I don't hit 50 frame per second. Just do the shift if I really need decimal numbers. That's it. I hope this answered the question. And I think that's it for my example.
You're not going
If
to
I
explain.
may, I don't know if you have time. I would like to show one of my old demo.
Before that, we have shown the example, but you haven't explained any code. Do you need to explain any code?
Oh yes, we can do. It's quite straightforward. We can do quickly. Yes.
Yeah.
Please open the third one.
Yeah.
And you go to line 143. And this is just really the only meaningful change. And here again, I check bit number 2 of DFF 016, and inside the branch there is first I apply the gravity. So mover apply force function is referred to the gravity. So first I apply the gravity to the mover object, and then I load the wind to the mover apply force function. If the mouse is not pressed, you just skip all this part, and the mover will just continue to go at a constant velocity like it was before. So it just, again, it's a Newton first law implemented, and that's it. Another very little change that I did on this part is at line 271, but it's not very interesting, just if you want to show it. But of course, this time, since we have the wind, the mover objects are moving to the right and to the left. So I had to say to the function responsible to calculating the position, okay, if you hit the right boundaries, you just invert the x position with the neg instruction again. So it's the same concept as before, but this time I had to do it for x. So if you hit the x position at line 279, it's the start. If x is greater than the right edge, you negate, so you multiply by -1, and you get the opposite direction. And if the x is lower than the left boundary, you just do the same thing, and that's it. It's just the very same concept, but I had to apply to the left and the right boundaries. Otherwise, the square will just continue on the left or on the right of the bit planes, and it won't crash because I set the clipping option at the top of the init function. So if the square, the vertex of the square is outside the bit plane's memory, it won't crash, hopefully, but still you won't see anything because they are off the screen. I think that I'm done for tonight with the examples. And
you said you use a demo, no? So if you can type the link in the chat, I can show
Yes, of course. Yes, you will need an Amiga with a lot of cheap RAM or fast RAM, at least 1 meg, maybe 2 is better. And this is not because the demo is heavy, is just because when I released this stuff, it was done on C language. But I want to show this demo to you because at that time I reused the same ideas and the same concept, only in C, but it's Amiga, so it works on a stock 1200, for example.
Oh, it didn't let you to paste.
I will send the link on the Telegram, okay?
Yeah.
And it's an ADF file, so it should be quite easy to load, and the loading takes a lot, a lot of time, but I hope.
Yeah, let's see.
And there is in this demo there is this gravity concept, and there is the wind concept and other concept that maybe I will explain in the future. It was just a proof of concept demo, so don't expect too much.
Okay, so how much chip RAM did you say it needs?
Yeah, just put 2 meg of chip and you should be good, or maybe you just say 1 megabyte of chip and some fast should do.
No, what I mean is also if it's an A1200 AGA, will it work or there will be issue?
No, it's an ACS production.
So I need the ACS.
Yes, you need ACS, but it works on AGA, of course, as well.
Okay, so I can run it on the same machine then. Okay, just not to spin up another VM. Amiga.
The only problem is the memory amount, which is not
sure,
well
no problem.
optimized.
Yeah. It's the problem of C, yeah.
It's the problem of C. I fought a lot with this problem. I ran out of memory, and I didn't understand why at the time. still today, the memory allocation on the Amiga is a mystery to me.
Really? Come on.
Yes, yes. I told you I was trying to make a short intro that runs on a stock A1000, which has only 256 kilobyte of chip, and part of that are eaten by the OS, and struggling to fit all this data inside such a tiny space.
Oh, I can run it from here. Sure.
Does it work?
I tell you in a minute.
You should see a loading screen with a strange face.
Yeah. I mean, it's not. Yeah, that's better, I think.
Yeah, this is the loader.
I just ran it from the workbench, so I don't know if it's okay or not.
Should be if you have
There you go.
fast RAM.
Oh,
Should be.
Margot.
Okay. So, as you can see, we have one big ball, and there is also the music, but I don't think it's necessary to show it. The concept here is I have these sprites. These are hardware sprites. There is one big ball, and the others are, of course, a smaller ball, and they are all affected by gravity because you can see. There is some force that is attracting to the bottom, and if you press, for example, repeatedly the key A, you should apply the wind to the left.
Yeah.
So just right.
I can understand already why you run out of memory.
Is gravity plus the wind to the left. And if you press the key S, you just reset the wind to 0. And if you press D, the wind is going to the right, and you can play with this.
I can see why you run out of memory or why you need a lot of memory.
There are a lot of assets here.
Yeah, the screen. You have a big image.
Yeah. I was testing how horizontal scrolling was working with the Amiga, and it was very long. I remember a lot of pain just to understand how this register works. And then when the animation is finished, the balls fell down, and that's it. So this is the important part of this demo is that I reapplied all the concept in this demo, but it is in C. But really, the math behind it is the same. So just maybe it should be interesting for someone. Maybe someone prefers doing this stuff on C. In this case, he can find all the routines inside this demo, which is, of course, open source. It's on GitHub. This is not related to what we talk at today. It's just a cube, just me experimenting with 3D. You can move the cube with WADS, and you can shrink it with Q and E if you want to play it.
What? Shrink it with what?
Q and E.
It's running on a 68030, so it's also why probably it's very smooth. I cannot imagine this on a 9500.
It works just like that in a stock A500. The only problem is
Memory.
the chip RAM to store all this music and all this
Yeah.
gorgeous artwork. But the line, the lines are drawn with the blitter, and the speed of the blitter more or less should be the same on the 500 and on the 1200. So I wouldn't expect much difference, even because I wrote this demo on my A600, and it works just like that, for what I remember.
Because the A600 has got to make one chip map, you know.
You can expand it to that size. I did it in the 90s. I spent a lot of money to get my extra chip RAM. And this is another concept, which is the friction. So the bolts are sliding to the ground, and they halt at a certain point. They stop because there is a friction force that is involved. And this is, again, not very interesting, but in the book Nature of Code, in chapter number 2, last paragraph, I remember that there is this concept of friction, and there is a slide, if I remember, with a slope, and just to illustrate what happens to the mover object if you go down the slope and there is ice, or if there is just some other material with affect the speed of the friction. But that's it. I think the instruction of this demo, because it's a very weird demo, it's an interactive demo. You can press things and the demo does stuff. I remember I coded this piece of software because we had a gathering in Central Italy for Amiga users, and I wanted to show my findings to my comrades, to my teammates. But in the middle, the COVID exploded, and this gathering was cancelled. And still, I released this demo in my GitHub and never shown to anybody. But I thought that could be interesting because today I talked about this very same concept. So. And that's it. And if you want to see, there is the very last part. I think it was about attraction. So you control the big ball, if I remember correctly, and the little ball is moving around because...
What are the keys?
The big ball... Please?
What are the keys for the big ball?
The keys are always the same. WADS.
But I'm controlling the small one, not the big one.
No, you are controlling the big one. Probably the window of your emulator is not active, and you are not getting
you're
input.
right. Yes, you're right.
Yeah, try to move the ball at the corner of the screen.
Upper corner.
Yeah, for example. And what I wanted to demonstrate here is that the big ball is the attractor.
Yeah,
and the little ball is just trying to be attracted by the big ball, and it forms this orbit around it.
So it's going to be attracted to the big ball.
Yeah, that was the goal of the code. I don't know if it gets the idea, but it should be attracted. Every time, at every frame, I calculate a difference of the vector difference between the big ball and the small ball, and this is the trajectory. And at every frame, I add this vector to the movement, and what comes out is something like that. And I would say that's it. The demo will restart and repeat endlessly. Okay, gravity kicks in, and I think that I have nothing more to show you. Sorry if it's not so comprehensive tonight.
Okay, so give me a second. So I'm just thinking. So we are finished, no? That's what you're saying?
Yeah, well, if you don't have any question, I will say we are done.
Anyone has questions? Anyone is still alive? Anyone is not sleepy? Anyone hasn't not got drunk yet?
They are coding.
Yeah.
They code all the night, and I don't because I sleep at night. I have to get up early.
Yeah. So, first of all, let's thank Ozzy, guys. Okay. Of course, Ozzy, I hope he will be back next week with another stream on demo coding. Probably he will send me the things in the last minute, and then I will be panicking. Guys, thank you very much. I appreciate all you having patience, listening to us, listening to Ozzy, and I hope you learned something. I am learning a lot, and Ozzy is giving me a lot of ideas. He cannot imagine how many ideas he's giving me. He thinks that his demos are stupid, but I don't think so, because everybody needs to start from something simple, and the simplicity of what he's doing is something that is giving me, pushing me to do some things. So thank you very much, Ozzy, and hope to see you all next week. Thank you. Bye bye.
You're welcome.